So we just saw in example 1 how we can use definite integrals to find the areas underneath curves. We're going to do the same process again in example number 2. We're going to begin by graphing the function and making sure that it's always continuous and that it's always above the x-axis on the interval 0 to 3. That's the interval we care about. So let's go ahead and do that. Let's make a graph. So to graph the function, you could just plug in y equal to x cubed plus x into your calculator, and then your calculator should show you something that looks like this. It extends on the other side, but we really don't care about what's going on the other side. We care about what's going on between the numbers 0 and 3. And by the way, when x is 0, the y turns out to be 0. That's the starting point. And when x is 3, the y turns out to be 3 cubed, which is 27, plus 3, which is going to be 30. So when x is 3, the y is going to be 30. So that's the area that we are interested in. It's basically bordered by these two lines, the one going from 0 to 0, and then 3 to 330. So those lines, we call them vertical lines, basically. And pretty much the space under the curve and the x-axis. So, let me go ahead and highlight it so that we can see what we're looking at. So there it is. This is the graph of the y equal to x cubed plus x, bounded by the x-axis and the two lines. So there you go. And so now what do you do to find this amount of space? How do you find the area of this graph? Well, you just do an integral. The integral is going to start at 0 because that was the lower bound of the problem. So 0 was there, so that's why we're putting it on the lower bound. And then the upper bound. So what's the upper bound in this case? The upper bound is 3 because that was the last part of the interval. So the lower bound is 0, the upper bound is 3. Perfect. And so now, once you do that, you're going to put the equation of the function in the middle, x cubed plus x, and then dx. That's pretty much how you find the area that you're looking for. Okay, so the area is an integral, basically. Now, to integrate, you're going to go term by term. What is the antiderivative for x cubed? It's x to the power of 4 divided by 4. So add this, add 1 to the power and divide by the same thing. Whereas for x, we do the same idea. That's x to the power of 1. So it becomes x squared over 2. And we said these are definite integrals, so no need to write down the plus c. You can, but it's a waste of time. It's going to cancel out eventually anyway. So we don't write down c. We just write down this little bar, and then we put 0 and 3 on the side. So what does this little bar mean? This is math notation. That means we're about to plug in 3 and 0 into the expression that we just wrote. And the order that we plug them in is by putting the 3 first, and then we put the 0 after. And we subtract the two solutions. So 3 goes in first, 0 goes in after, and we subtract. By the way, this is a super important theorem in math. This thing that I just wrote is called the fundamental theorem of calculus. That's the name of what I'm doing right now. There aren't that many things in math called fundamental, and so when you hear the word fundamental, you should think this is really, really important. This is like one of the most important theorems that you can ever have in mathematics. The theorem that says we can do all the process that we're about to do, right? So at this point, all this can be just plugged into the calculator. Just click enter, and let's see what happens. So when I do this, I end up with 99 over 4. That's my solution for all of this. So the fundamental theorem of calculus is basically used to say that definite integrals can be evaluated by doing the antiderivative, then plugging in the upper bound, and then plugging in the lower bound. So the 3 steps that we did here are basically called the fundamental theorem of calculus. And why do we do the fundamental theorem of calculus? Because we want the area underneath a curve.